Okay, we'll start with the problems from your review sheet, and then we'll cut and we'll go over to the weighed problems. So the first question, which of the following statements best describes the relative bond dissociation energies of sigma and pi bonds present in the carbon-carbon double bond of an alkene? Okay. So the idea here is that a carbon-carbon double bond is made up of two bonds that have different characteristics, different properties. The first bond is caused by end-on-end overlap of an orbital. So if we've got a carbon with some orbital and its electron in it, and we've got another carbon with its own orbital and its own electron in it, we can bring these together and get overlap where the electrons kind of reside in both orbitals. So end-on-end overlap, where the two orbitals overlap end-on-end, we call that a sigma bond. And also, though, in certain conditions, the carbons also have orbitals that lie parallel to each other. So if here's one carbon, it has an orbital that kind of looks like this, like a figure eight. Sometimes you call it a barbell, like this. So if there's already a sigma bond present, there's our sigma bond, then these side-by-side orbitals that each contain their own electron can also overlap side to side. And that overlap occurs from the top lobe and it occurs from the bottom lobe. So don't think it's just one or the other, it's both. And we call this a pi bond, where half of the pi bond is above the plane and half of the pi bond is below the plane. So that's the main difference between a sigma bond is end-on-end overlap. A pi bond is side-to-side overlap. You get a lot better overlap from end-on-end overlap. So sigma bonds are stronger. Pi bonds, the overlap side-to-side is very weak, so the bonds are weaker. So what we mean by bond dissociation energy is the energy that it takes to break that bond. Okay, so if we've got, a sigma bond that we're going to then break, the idea is we're going to take one electron and break it and put it onto one carbon. The other electron goes onto the other carbon. So that's what we're doing. We're breaking this bond symmetrically. And we produce what are called radicals. Okay. So that's the process for bond dissociation energy. So this is going to require an input of energy, BDE, bond dissociation energy. It requires an input of energy because the bond is stable, we have to break it. So since the sigma bond is more stable than the pi bond, the bond dissociation energy will be higher for the sigma than the pi. So the answer is A. Sigma bond requires more energy to break than the pi bond, okay, for all the reasons we just talked about. Question 2. Which of the following best approximates the bond angle, the CCC bond angle, in propene So first thing we have to think about is what is propene? The prop means 3 carbons. The ene means we have a double bond somewhere. And in propene, that double bond can really only be one place. So that's propene. And so looking for this, this particular bond angle, There, that angle. The trick that you have to know here is that the bond angle is basically related to the number of electron domains around the central carbon. So this carbon in the middle is going to dictate all of the angles to it. And so that is that's the carbon that we're going to focus on. So I mentioned this term, electron domains. An electron domain is some region in space around an atom where there is electron density. So around this central carbon, there are 3 electron domains. There's the electron domain to the methyl group. Okay, this bond, that's 1 electron domain. The bond to the H, that's another electron domain. And then the double bond, interestingly, the double bond counts as a single electron domain because the sigma and the pi bond, like we saw in question 1, the sigma and the pi bond exist in the same region of space. Okay, they are both between our focal point carbon in the middle and this methylene group, the CH2 group on the side. Okay, so that's 3 electron domains. And the trick is to remember that 2 electron domains is 180 degrees. 3 electron domains is 120 degrees. And 4 electron domains is approximately 109.5. There can be some slight variation there from 109.5 down to about 104.5, depending on whether the domains are lone pair domains or whether they are bonding domains. The angle can vary a bit. But if they're all bonds, then we follow this pattern exactly. So 3 electron domains around our central carbon. Right there means that the bond angle around that carbon is going to be 120, and that's exactly what they're looking at for this problem. 120 degree bond angle. All right. Question 3. What 2 atomic orbitals or hybrid orbitals overlap to form the CH bond in ethylene? All right. So again, first you have to know the name. This is kind of not strictly IUPAC. But it's common enough that most people use it interchangeably. Ethylene is also known as ethene, which is 2 carbons so 2 carbons F, ene means double bond. So what they're asking for is what orbitals are being used to make these CH bonds. They're all the same. So in order to know what the orbitals are being used, we have to know what the hybridization is. And just like in question 2, the hybridization is related to the number of electron domains. So I'll write this up here. 2 electron domains, 180 means sp hybridization. 3 domains, 120 equals sp2 or sp squared hybridization. And 4 electron domains, 109.5 means sp3. All right. So, but hydrogen only uses S, right? Hydrogen only has its 1 electron. So that 1 electron can sit purely in the s orbital. There's no benefit for that orbital to mix with anything. But the carbon, normally carbon would have the s orbital, and then the 3 equal p orbitals at its disposal. But when carbon bonds, it's actually better off if it mixes those orbitals first. That way, every single bond gets a little bit of s character. So we're going to mix this s orbital into the other p orbitals, and we're going to mix them all together. But the rule is that, or the logic is that carbon will only mix as many orbitals as electron domains that it needs, because the more mixing we do, the more p character we get. Every time we mix in another p orbital, we get more p character, and that makes the energy higher. So if we only need two connections, if we only need two domains, we only need to mix two orbitals, and so we get 50% s character by mixing an s and a p. If we need 3 electron domains, we need to mix 3 orbitals, so we mix s with 2 p's and we get 33% s character. If we need 4 electron domains, then we need to mix the s with all 3 p's, and we're left with 25% s character. The idea being there is that when we do that, every orbital gets 25% s character, as opposed to if we didn't mix it, 3 of the 4 orbitals would have no s character whatsoever. All right, so that's the quick and dirty logic for why hybridization occurs. So here we should recognize that if we're looking at an H to C bond, we know that the H is always going to be using an s orbital. But this carbon, we have to say what type of orbitals is it going to use. So there are 3 electron domains. That carbon has an electron domain to one H, an electron domain to the other H, and then the double bond again counts as a 3rd electron domain. So 3 electron domains, again, sp2, means that we are going to mix an s with 2 p's. And there we're going to have 3 equal sp2 orbitals. And then the 1 p that's left over, so the higher energy p orbital that's left over. So those are our 3 sigma bonds, okay? So one of our sigma bonds will come from an sp3, another sigma bond will come from sp3, the 3rd sigma bond will come from sp3, and then the pi bond comes from the p, okay? So this pi bond between the 2 carbons, that is using the p orbitals from each carbon. But specifically, we're looking at the sigma bond. We want the sigma bond between the hydrogen and the carbon, and that is going to be using an sp2 orbital. All right, so that is a carbon sp2 and a hydrogen H is what we're looking at here. Okay, provide the IUPAC name for the alkene shown below. So it's a cyclic molecule. It's 5 carbons, 1, 2, 3, 4, 5. When we number a molecule, we are always going to try to prioritize any functional groups there. So we only have one functional group here. We're going to prioritize the alkene. So we would number it through the alkene, starting on the alkene and numbering through it like that. So we've got 5 carbons with the alkene between 1 and 2. And then normally we would indicate where the alkene is. So this would be cyclopentene. And I'm going to leave this blank here for a moment. So let's just remember the logic. Cyclo means it's a cyclic structure. Pent means it's 5 carbons. And the ene means we have a double bond. We have an alkene. Normally, we would indicate where that double bond is with a number like, pent 2-ene or something like that. In this case, kind of by definition, though, the alkene will always start on the 1 carbon. There's no real other option. We always number from the alkene. So technically, you could call this cyclopent 1-ene, but the 1 is redundant. We know it's got to be on the 1, so we just omit it. And it's just cyclopentene. Okay. Just as a reference, kind of what we're getting at here is that if you have a linear structure, something like this, Now we prioritize the left side of the molecule so that the alkene starts on carbon 2 and goes to carbon 3. And now specifically we need to indicate that the double bond is on carbon 2. So this would be pent 2-ene. So now the location of the double bond is relevant because it could be in different positions. It could be on between the 1 and the 2, between the 2 and the 3. Those are two different options. With the ring, it always by definition starts on the 1, unless there's something else going on. But with just a plain old boring ring, it always starts on the 1. Okay, number 5, for which of the following alkenes will cis and trans isomers not exist? So what cis and trans mean is when you have a double bond, let's say that we have a methyl group and a methyl group and a hydrogen and a hydrogen. That double bond could exist in two different geometries. Where we have the methyl group like that, and then up here. Like that. Because of the fact, let's go back to our picture of a pi bond, or our very rudimentary picture of a pi bond. Because of the fact that the pi bond requires that the orbitals overlap side to side, a pi bonded pair, an atom pair that's pi bonded, can't rotate around that bond. Okay, the pi bond is rigid. There's no rotation, because if it rotated, it would break the bond, and it just doesn't happen. There's not nearly enough rotation energy to cause a pi bond to snap. So we can consider these molecules rigid. One of them is locked across that pi bond with the methyl groups. Notice that the methyl groups are kind of close to each other. We call that cis. Okay, so what we're specifically looking at is the groups on one carbon, say the groups on the green carbon, versus the groups on the yellow carbon. Okay, that's kind of our reference. So the methyl on the green we say is cis to the methyl on the yellow. Okay, and it's locked in that position. In the bottom structure, we've got the green carbon and the yellow carbon. And now the methyl carbon on the green is trans. Okay, it's across the double bond. That's called trans. And again, it's locked in that position. Okay, so in order to have a cis and trans option, which we call isomers, these are isomers because they're different structures. They're different molecules. They can't interconvert. Because they're locked. That rotation is locked. You have to have dissimilar groups on the green carbon and on the yellow carbon. If you have identical groups on one of those carbons, there's no way that you can have cis and trans, right? For example, looking at A, we've got chlorines over here. So there's really no cis and trans. Like this H is trans to the chlorine, but it's also cis to the chlorine, right? If you swap those groups, right? If you were to swap these two groups, you get the same molecule. It's literally the same thing. Whereas over here, if we swap these groups, we get something different. We get cis versus trans. So A doesn't work because we've got those two chlorines. What else do we have? All of them work then. So notice that in molecule B, on one side we've got a methyl and an H, and on the other side we've got a methyl and a chlorine. So you can imagine that if we swapped these groups, Or if we swapped these groups, you get a different structure. You'd have the methyls cis, in this case, they're cis. If you swapped one of the groups, like if you swapped this methyl with this H, then the methyls would be trans. So B has cis and trans isomerism. So B's okay. Same thing with C, right? Over here we've got a methyl and an H, and over here we've got an ethyl and a methyl. So as drawn here, you can see that the methyls are trans to each other. Or you could also think of it as that the methyl is cis to the ethyl, if you wanted to think of it that way. That's fine too. Cis and trans are relative terms. You're just talking about the relative position of two groups. So you've got in this case, we've got the methyls that are trans, and then we've got the methyl that's cis to the ethyl. But if we swap these groups, if we swap these guys, then we have something different. Now we've got the methyl cis and the ethyl and methyl trans. So that's got cis and trans isomerism. And then over here, same thing. Notice that even though we've got two chlorines, they're on different carbons. That's okay. What we have to make sure is that each carbon has dissimilar groups. So in this case, we've got the chlorines that are cis to each other, and we've got the methyls that are cis to each other. If we swap those, if we swap the groups on one of these carbons, then the methyls would be trans and the chlorines would be trans, right? So that has cis-trans isomerism. So A is the only one here that does not have cis-trans isomerism. A only. So again, if you are looking at each carbon that's involved in the double bond, okay, that carbon cannot have identical groups on it. Or I mean, it can, but then it just doesn't have cis and trans isomerism. Okay, I think that's clear. All right, question 6. Which of the following best describes the geometry about the carbon-carbon double bond? So here we're using a slightly more precise notation. Cis and trans, like I said this before, cis and trans gives us a description of the relative position of two groups across a double bond. We can say, are the methyls cis? We can say they're cis to each other. Or we can say, a methyl and a chlorine are trans to each other. It's a relative designation. E and Z, we get a little bit more precise. So let's look at this from two perspectives. We want to look at this as having the blue carbon, and we're going to look at this as having the red carbon. Okay. So what we're going to do, we're going to treat these as separate entities for now. And we're going to evaluate the groups that are attached to each. And we're going to rank them basically based on what we call stereochemical priority. If you don't remember stereochemical priority, we basically rank it by which has the closest atoms that are also the heaviest. Okay, the closest bonded atoms that are also the heaviest. So to do this, we'll look at the blue atom. Blue atom is attached to a C, and that is attached to 3 H's. Okay. Over here, it's attached to a C, and that C is attached to 3 H's. So those are identical. There's no way that we can differentiate them. So we would rank that as a 1, and we'd rank that as a 1. Okay, on the other atom, on the red atom, we've got a chlorine and a chlorine. And of course, those are equal. Okay, so we'd rank those as a 1 and those as a 1. Okay, when you have a situation like this where you hopefully identify that you've got equal groups, and so you don't have cis and trans isomerism, you can't have E or Z geometry either. Okay, Those are equal in kind of priority on one carbon. Now, if that wasn't the case, if we had something like this, where we had a C double bonded to a C, and we've got let's do this. We've got a hydrogen and a fluorine and a chlorine and a bromine. Here's the point with E and Z. You could talk about relationships being cis and trans. We could say that the H is cis to the bromine. Or we could say that the H is trans to the chlorine. Right? Or we could say that the bromine is trans to the fluorine. Right? Any of these relationships could be described. But if I were to ask you what the geometry of the double bond is, if I were to say, is the double bond cis or trans? That doesn't make sense now. We say, well, what is cis, right? It doesn't matter, or it doesn't make sense anymore. So we need to be a little bit more precise, and that's where we use E and Z. So again, we're going to rank these. On the left side, on the blue side here, which is higher priority? Well, the fluorine is heavier than the H. So we're going to rank the fluorine as 1 and the H as 2. On the red side, the bromine is higher molecular weight or atomic weight than the chlorine. That's a 1 and the chlorine's a 2. So now notice that we have different rankings, unlike what we had over here. We had equal rankings on one side. In fact, we had equal rankings on both sides. But as long as we have equal rankings on one, we can't have cis or trans. But now, we're going to imagine slicing this right through the alkene. And we ask ourselves, are the ones on the same side or are they on the opposite side? And clearly they are on the opposite side. One here and then one here. So we have to cross this line to connect the ones. If they are on opposite side, it's called E. E stands for the German word entgegen, which means separate or apart. If they are on the same side, or if they're together, for example, if we had a structure where we had like 2 and 2 and 1 and 1, something like that, right? Now the 2s are, if we slice through the double bond, the 2s are together, the 1s are together. Okay, if they're together, we call it Z, which comes from the German word zusammen, which means together, basically. The way I remember this, Z, they're on the same side. Right? If the ones are on the same side, it's Z. If they're not, it's E. Okay? So in this case, in the example given, it's not E or Z because we've got equal groups on each carbon. All right. Next one, circle the alkene below, which has the smallest heat of hydrogenation. So this is one of these situations like the bond dissociation energy, where we have to know what that quantity refers to. We have to know what process is described by that quantity. And for heat of hydrogenation, what we're doing is this. I'm going to open a new note here so I can draw something. What we're doing is we're going to take an alkene and we're going to convert that alkene into an alkane. Okay, so here we've got 1H on that carbon and 1H on this carbon. We're going to use up that pi bond and fill it in with another bond to H on each carbon. That's heat of hydrogenation. Usually you do this with a reagent like H2 and a catalyst like platinum, for example. But since we've got a pi bond here, right? The second bond in the double bond is a pi bond, and we're getting rid of it. We're converting it into sigma bonds, right? We're taking a weaker bond and we're making it into something more stable. So the energy of the alkene, if we were to kind of graph this with the energy, okay, the alkene is higher in energy than the alkane. So this is alkene. Alkane. So we're going down in energy. This process is downhill. And so this difference, the difference between that delta E is the heat of hydrogenation. All right. So this is very interesting because a large delta E means that the alkene is unstable. Right? In order to have a large delta E, your starting point has to be very high so that our change is very large. Okay? So remember, with bond dissociation energy, we were putting in energy because we had to break a bond. We had to take a stable bond and break it into two pieces. Here, we're taking an unstable bond and we're converting it into more stable bonds. So this is releasing energy. Okay, so it's opposite logic. I guess it's the same logic, but we're going in the opposite direction than we were for the bond dissociation energy problem. So here, if we're looking for smallest heat of hydrogenation, that's the smallest gap. So we're starting from a very low position to begin with, and we're just going a little bit lower in the reaction. So what this is really getting at, if they're really asking for, or if they're asking for the smallest heat of hydrogenation, we're looking for the most stable alkene, the most stable pi bond, to be specific. And without going into too much theory, the most stable pi bond will be the most substituted. So that means the most carbons attached to it. So let's do a quick count here. The first double bond only has 2 carbons attached to it. Over here we have just H's, so we don't count those. Here we've got 4 carbons attached. All right, here we've got 2 carbons attached and then 2 H's, so we ignore the H's again, but they're there. And then here we also have 2 carbons with the 2 H's. So only the second one is, we call it tetra-substituted. All the other ones are di-substituted. Okay, so that's going to be the most stable double bond. It's going to require the least amount of energy, or it's going to release the least amount of energy when that pi bond is converted to sigma bonds. All right, question 8. Does the alkene below violate Brett's rule? Okay, so Brett's rule is a rule that applies to bridged bicyclic alkenes. So this is what a bridged bicyclic molecule looks like, something like this. Notice we've got two rings. We've got a 6-membered ring. 1, 2, 3, 4, 5, 6. We've got that 6-membered ring in pink. But we've also got a 5-membered ring. 1, 2, 3, 4, 5 in orange. So there's two rings. And the two rings kind of are intertwined by a bridge. Okay, that blue thing there, that's a bridge. In this case, it's a 1-carbon bridge. There's only that 1 carbon at the top. So it's a 1-carbon bridge. But that's a bridged bicyclic alkene. And Brett's rule specifically applies to this type of thing, where Brett's rule says that you cannot have a double bond on a bridgehead carbon, which are these. These are bridgehead carbons. They are the carbons that are participating in the bridge. Brett's rule says you can't have an alkene on the bridgehead unless one of the rings has 8 carbons or more in it. Okay, which is seems a little bit of an obscure rule. Let me explain why. I'm going to redraw this. And it might look perfectly normal for me to do this, to plop a double bond there. But there's a problem. It's a sleight of hand, okay? Because what I've done by putting a double bond there is I've made a trans double bond. Look at this geometry here. 1, 2, 3, 4. See that? That's a trans double bond. Trans double bond. And that's a 6-membered ring. I've literally just drawn a trans double bond in a 6-membered ring. You can't do that. Think about what a 6-membered ring looks like. Here's a 6-membered ring. Any double bond in a 6-membered ring has to be cis, right? If I try to draw like a trans double bond in a 6-membered ring, it would have to look something like this. Something, I don't know, like there's a trans double bond. It doesn't work, okay? There are not enough carbons in the ring to accommodate a structural deviation that's required by the trans double bond. So here's the idea. You can't have a trans double bond in a 6-membered ring. You can't have a trans double bond in any ring unless that ring has 8 carbons or more, okay? By the time you have 8 carbons or more in a ring, there are enough carbons to accommodate that trans geometry, okay? So Brett's rule is a little bit of a shortcut that says, hey, be careful. If you've got a bridgehead carbon, don't get fooled into putting a double bond there unless that ring involves 8 carbons or more. All right. That's Brett's rule. You can't have a double bond on a bridgehead carbon unless the ring has more than 8 carbons, because it is implicitly making a trans double bond, which is not allowed in smaller rings. So the answer to this question is no. This does not violate Brett's rule because our molecule does not have a double bond on a bridgehead carbon. Okay, piece of cake. If you know what Brett's rule means. Okay, very easy to spot. The next question, though, a little bit more tricky. And there's 2 ways you can look at this. First of all, this is not a bridged bicyclic molecule. There's no bridge. It is bicyclic, but it's not bridged. Okay. So kind of off the bat, you can say, well, Brett's rule doesn't really apply because it's not a bridged bicyclic molecule. But notice that we do have a trans double bond here. Even if you think about this as being a bridge, and you think about these carbons as being bridgeheads, and you say, well, don't we have a double bond on a bridgehead carbon? Sure we do. But that's a 10 carbon ring. Okay. The ring, if you look at the 6-membered ring, okay, there's a 6-membered ring. The double bond within that ring is cis. No problem. We do that all the time. If you look at this ring, though, okay, now the double bond is trans in that 10-membered ring, but it's more than 8. So that's okay, right? So no, it doesn't violate Brett's rule. Okay. Whether you want to think of it as being just like a bridged bicyclic molecule, but we've got more than 8 carbons, so it's okay. Or you can say, well, it's not a bridged bicyclic, so it can't violate Brett's rule. That's fine too. Either way you want to think about it, it works. So that does not violate Brett's rule. The point is, you just have to be careful. You have to ask yourself, does my double bond create a trans geometry? And if it does, is that trans geometry in a small ring? Okay, if it is, then you've got a problem. That structure is not real. Okay, so none of these do. All right, dehydrohalogenation. This is a shorthand. This is a long, complicated word for E1 and E2 mechanisms. Okay, when you learn E1 and E2, specifically E1, E2, where you lose an H and a halogen. Okay, so, we've done simple eliminations where we've got a halogen and a base removes a neighboring hydrogen. Electrons fall in, push off the chlorine. That's a dehydrohalogenation. We are removing an H and a halogen. Okay, so that's E1, E2, where you are losing H and X. Okay, so actually 2-bromobutane. Let's simply replace this with a bromine. Okay, so dehydrohalogenation of 2-bromobutane. Again, you want to know that name. 4-carbon chain is butane with a bromine on the second carbon. In the presence of a strong base and heat. Okay, so strong base means charged. Something like OH minus or OCH3 minus or OTBU minus. Okay, these are oxygen bases. You can have nitrogen bases too, but the point is that they have to be charged. You have to have a negative charge. And heat. Remember that heat favors elimination. If you work through our flow chart, the first question I ask in our flow chart is, do you have a charged base or nucleophile? And if the answer is yes, you always end up in the second order pathway. So here you would say, okay, is my base or nucleophile charged? You'd say yes. The next question is it methyl or primary? You'd say no. Then you'd say, is it secondary? You'd say yes, because our halogen is on a carbon that contains 2 carbons connected to it. So it's secondary. You'd say yes. The next question is, do you have heat? And if the answer is yes, then you end up with E2. Okay, so strong base means second order. Dehydrohalogenation means E1 or E2. So they're looking for an E1 or E2, that's second order, which is E2. Okay. I think that's pretty straightforward. Propose a synthesis for the following. Okay. So synthesis kind of implies that there's going to be multiple steps. We have to do one transformation followed by another, perhaps followed by another, where the product of the first transformation acts as the reactant for the second transformation. And usually in these types of problems, I like to recommend working backwards, logically working backwards, meaning ask yourself, what's the last step that I need to do? Let's worry about the last step first. And then once we're there, we can work backwards from that, and eventually we'll get back to our starting material. So the product of this is an alkane. And we really haven't done much that involves making alkanes. Usually we start with alkanes and we make them into something more interesting. In this case, we're trying to make an alkane. And there's really one reaction that is relevant for making just a plain boring alkane. And that is hydrogenation, which was one of our previous problems, where we say, okay, if we start with a double bond, and then we add H2 and platinum, or some other catalyst, palladium, something like that. Remember, that will hydrogenate the alkene. So if our goal is an alkene, if our goal is an alkane, probably the last step would involve converting an alkene to the alkane. Okay, that's really the only reaction that is relevant at this point. Then we have to say, all right, well, how could we make the alkene? If our second to last step, we have to have an alkene, how can we get there? So we actually know a reaction or a type of reaction that would convert the alcohol into the alkene. It's called dehydration. Where you first convert the alcohol into water using acid. Actually, it's not really two steps. So we use acid, H3O plus. That converts the alcohol into water. And then water acts as the leaving group. So this is like our leaving group. Okay, where something, probably another water molecule, grabs the adjacent H, the electrons fall in, and push off the leaving group. Since water is leaving, you need heat. You need heat to drive off that water. So H3O plus and heat are the reagents that you need for a dehydration. Okay. And that will essentially just eliminate the alcohol as if it was any other elimination. Alcohol itself, an OH, is not a good leaving group, so we add acid to convert it to a good leaving group. Okay? So we do the elimination to get the alkene, and then we just hydrogenate the alkene to get the alkane. As you will discover, as you learn more reactions, there will inevitably be more answers to these types of syntheses. There are definitely more than one way to do this transformation. At this point, you haven't learned all the reactions that you will eventually learn. So there are more ways to do it, but from the reactions that you should have learned at this point through the alkene chapter, this is the way to do it. Okay. By the way, this OH doesn't have to be an OH. If it was a BR, we could kind of do the same thing. We wouldn't do a dehydration. We would do a regular elimination, a dehydrohalogenation. Eliminate the BR, make it into a double bond, right? And then hydrogenate the double bond. So the starting material is just providing us with some functionality. Okay, we're going to use that functionality to convert into something that will eventually get us to get us to an alkane. All right. Let me see. Is that it? So we're going to jump ahead here. Okay. We're going to jump to we did all these together. It was these. So you and I did not do these. And remember, this answer to this one was found on Wade. Page 415 and 416, right? So you can find that there. All right, but the other ones that we didn't do was were these two, looks like. I think, were there more after this? Oh, there were a few. Okay, so we've got a few more mechanisms here. Yes. Okay. So here we've got an interesting reaction. An alkene reacting with HBr, and this ROOR, ROOR, this is a peroxide, this OO bond is a peroxide. So here they're just specifying a generic peroxide. It could also be hydrogen peroxide, HOOH, or H2O2, right? That's hydrogen peroxide. The point is that you need a peroxide of some kind for this. So HBr with a peroxide. There's also a reaction that doesn't include the peroxide. It happens very differently without the peroxide. And we've got an alkene. That's our functionality in our starting material. So here's the mechanism. And this mechanism you can find in your textbook. But I will walk you through it and explain what's going on here. So the first step, before anything else, is that peroxides, also heat. Heat kind of facilitates this. So under warm conditions, the peroxide will dissociate. Into two radicals. This is literally the definition of bond dissociation, where you take a bond with its two electrons and you cleave it symmetrically. Okay. So one electron goes onto one half, the other electron goes onto the other half. Okay. That's the first step. This is going to make, these are called radicals. And this is going to dictate how the mechanism goes. If you don't include peroxide, you don't form radicals, and then everything else happens differently. But once you create the radicals, then everything gets going. So what happens in the next step is that one of our radicals will react with our HBr. And here you have to remember, how does it react? what we're going to do is we're going to take one electron from the radical and one electron from the bond. And then the other electron goes on to the Br. Okay. So specifically, this makes ROH, right? And then Br radical. Br dot, as we might say. Okay. The idea here is that I'm going to get cute here. So here's our person. You're going to remember this. Br dot more stable than H dot. Okay. A hydrogen radical, just a hydrogen atom basically, is fine, but it's either one electron shy of having a full shell, which would make it H minus, or it's one electron shy of having an empty shell, which would make it H plus. Bromine with a radical, it has what, 35 electrons as bromine. It would like bromide, so it would like to be 36 electrons, and it's got 35. Bromine barely notices the fact that it's a radical. Okay, the amount of electrons that it's got relative to the amount of electrons that it's missing, which is 1 basically, is minuscule. Okay, it's got 35 out of 36. Hydrogen, it's a much bigger deal to be a radical because it's 50% off of where it wants to be, right? From either having 2 or having none. So Br radical is more stable than H radical. And that's why the RO radical pairs up with the electron from the H and leaves the bromine all by itself. Okay. If the RO radical picked up the bromine, then it would leave us with H radical, and that would be much less stable. So that's how you remember that step. Okay. The RO picks up the ROH, or picks up the H to become ROH. Now the alkene comes into play. So for our third step, we're going to take our alkene, and the bromine radical is going to react with the alkene. So we're going to take one electron. Remember, the alkene is a sigma bond and a pi bond. The pi bond is weaker than the sigma bond. So one of the bonds will react and the other one won't. The pi bond will react. So what we're going to do is we're going to take one electron from the radical and we're going to pair it up with one electron from the pi bond. Okay. The other electron, and this is very important, the other electron goes onto the more substituted carbon. Okay. So radical on more substituted carbon. So here again, look at what we have here. We've got our green carbon has 2 carbons on it. Our yellow carbon only has the hydrogens, right? So when we take one radical, or one electron, excuse me, and pair it up with the bromine, where does the other electron want to go? It wants to go onto the carbon that can stabilize the radical the best. The other option would be to put it over here, where it's less stable, right? So we're going to put it onto the carbon that's more stable. And then the bromine is going to go on that other carbon. Okay, so here, we're going to put the bromine on the less substituted carbon. So it's still got its 2 yellow H's, right? Those 2 yellow H's are still there. So that's that bond we made, that blue bond, right? That's our new bond. By bringing 1 electron from the bromine and pairing it with 1 electron from the pi bond, right? There's our new bond. And then the remaining electron that we unpaired goes on the more stable position. Okay. Like that. And then that radical will react with another HBr. And it's going to react in the same way that our first radical did, where this radical is going to pair up with, we're going to take 1 electron from that, use a different color. We're going to take 1 electron from our radical here, 1 electron from the bond, for specifically, and we're going to pair it up with the H. And then the other electron goes on to the bromine. And so the reaction can continue. Just like we made a bromine in step 2 from the peroxide radical, here we're making another bromine from our alkyl radical. But the point here is that we get a neutral organic product. Okay. And then again, we've got the Br dot that can go on and do more reactions. So this reaction will kind of self-propagate. It's a chain reaction where we create a radical from our peroxide originally. That radical goes on to make a new radical. That radical goes on to react to eventually make more radicals, and the reaction continues. But here's the product. And there's a very important pattern here that if we go back and look at our original alkene, okay, this carbon is primary. This carbon is tertiary. Okay. Or another way to look at it. Okay, this carbon has 2 carbons on it, right? It's the more substituted one. And this carbon has fewer carbons on it. So in this reaction, okay, these conditions, the bromine ends up on the less substituted carbon. The bromine ends up on the primary. The H ends up on the tertiary. Okay, that is called anti-Markovnikov. It's unfortunate that we got to anti-Markovnikov first. Usually when you learn this, first you learn Markovnikov's rule. Markovnikov's rule says the opposite, okay? Markovnikov's rule says that when you add something to an alkene, the H goes on to the carbon with the most H's. Think of it like safety in numbers, or the hydrogen likes to go with its friends. Okay, the H, Markovnikov's rule says that the H goes on the carbon with the most H's. Here we violated that rule because we put the H on the tertiary instead of the primary, which already had 2 H's on it. Okay. So this violates Markovnikov's rule. So we call it an anti-Markovnikov reaction. Remember earlier in our lesson, I had said that mechanisms are important. You have to learn them because you'll either be asked about them explicitly or you'll be asked a problem that requires you to know the mechanism in some form. But you also want to learn the big picture. You also want to learn what the transformation pattern is that is caused by the mechanism, okay? Because in this type of a problem, here they happen to give us, they happen to ask for a mechanism, but they could have very easily just asked for the product. And in that case, if you can look at the double bond and go, okay, I've got a more substituted side and a less substituted side, and I've got reagents that force Markovnikov, or they force anti-Markovnikov. Then all you have to do is put the H on and put the Br on. And you just have to decide which carbon is the right carbon. And you know, if you know Markovnikov's rule, and you know that if the reaction obeys it or violates it, it's very easy. So you can get to this product if you know the pattern. You can get to this product in literally like 5 seconds without the mechanism. Okay, if you have to draw the mechanism in order to figure out the product, you're going to waste all your time drawing arrows. Okay, so learn the mechanism so that you remember how the reaction works. You can run through it in your head if you have to, but try to not rely on the mechanism or not rely on drawing the mechanism to help figure out your answer. Okay, so that's anti-Markovnikov, where the bromine goes on the less substituted carbon. So in this reaction, without having to go into all the nitty-gritty detail, it's ultimately the peroxide that causes this. It's the ROOH that forces us to go through a radical mechanism, and it's the radical mechanism that produces the anti-Markovnikov result. Without the peroxide, like we have in question 25, it follows Markovnikov's rule, okay? So HBr just by itself is a Markovnikov reaction. So here's how this works. It's much simpler. I'll draw it out here. So here's our alkene, and we've got HBr. No peroxide, so no radical formation. Instead, what's going to happen is the pi bond, instead of going through a single electron pattern, like it did with radicals, is going to use both of its electrons to grab the H and put the electrons onto bromine. Again, bromide is stable, so it's going to grab the H to produce Br minus instead of grabbing the Br to produce H minus. Okay. Plus the H, to get into a little bit more analysis, the H is it has some positive character because the bromine is electronegative. So the H is positive and the pi bond is electron rich. Or the double bond is electron rich. It's got 4 electrons in that domain. So that negative rich double bond will be attracted to the H because that H has some positive character. So now the question is, which carbon gets the H, right? Since this pi bond is sitting between both carbons here, the H can only go on one carbon. We have to choose one. So we follow Markovnikov's rule. Markovnikov's rule says the H goes onto the carbon with the most H's. And in this case, there's an H there. So why does it do that? All right, why does Markovnikov's rule exist? Well, let's see. When we do that, if we use the pi bond, and put the H there. Okay. Then the other carbon is left missing a bond. It lost its pi bond, but it didn't get the H in return. That is a tertiary cation, which is very stable. If we were to go the other direction, if we were to violate Markovnikov's rule in this reaction and put the H here, then we'd end up with a secondary cation. Then the other carbon would have the positive charge. And that's not as good. Okay? So the H will go onto the carbon with the most H's, because that leaves the carbon with the most carbons, the one that has the positive charge. Okay, so that is the origin of Markovnikov's rule, to make the most stable intermediate. Okay, then from this point, we've got bromide floating around. And it's very simple. Bromide is going to come in and add to the cation. So that's the Markovnikov pattern. Okay, that's it for the reaction. It's very simple. It's 2 steps. H protonates, make the most stable carbocation. You know, put the H wherever you need to make the most stable carbocation, and then the bromide attacks the carbocation. Let me compare these two just for the sake of completion here. The reason why the pattern is opposite, the reason why we get anti-Markovnikov when we use peroxide, but we get Markovnikov when we do not, is that in the peroxide pattern, where it is, in the peroxide pattern, the bromine goes on first, right here in our 3rd step. The bromine goes on first and makes the tertiary radical. See that? We still get the octet deficient species on the more substituted carbon. But we do so by putting the bromine on first, because we have a bromine radical at this point. In the Markovnikov pattern, we put the H on first. So the H goes on there, as opposed to the bromine going on there like we did the first time. Okay. So the H goes on first to give us the tertiary cation. The octet deficient species is on the tertiary carbon again. And then the bromine comes on second. Okay. So the presence of the peroxide and going through the radical mechanism ensures that we have free bromine before we have free hydrogen. Okay, that's basically it. But learn the pattern, okay? Learn what the Markovnikov pattern is, which is H goes on the carbon with the most H's. Very easy. H goes on the carbon with the most H's. Anti-Markovnikov is the opposite, where you violate that rule. It's kind of like Zaitsev and Hoffman. You learn the Zaitsev rule, and then you learn when you violate it. Okay. So here's a very fun kind of extension of that reaction. Draw the major organic product generated in the reaction with step-by-step mechanism. Pay attention to regio and stereochemistry detail. Okay, so we know how this is going to work, basically. HCl, like HBr, with no peroxides, with no peroxides means it's a Markovnikov mechanism. So let's draw this out. HCl. The pi bond is going to grab the H, kick off the chloride. We're going to put the H onto the carbon with the most H's. Okay, so if we analyze the carbon on that side of the double bond and the carbon on that side of the double bond, the carbon on the left has one H, the carbon on the right has two H's. So Markovnikov's rule says we're going to put the H on the carbon with the most H's. So we're going to have three H's here now, 1, 2 plus our third. And that's going to leave the other carbon with the positive charge. So it's secondary in this case, and that's also very important. It's a secondary carbocation. Versus if we had gone the other way, if we had put the H on the other carbon, we would have ended up with a primary carbocation, right? So secondary is better than primary. Now, this is also why you learn mechanisms, because this problem is going to involve a deviation to our mechanism. Normally, under normal conditions, let's just remember how this would normally happen. Chloride would then simply come in and attack. And we would get this. We'd get what you might call the expected product. Okay? That's expected, maybe. I'm putting that in quotation marks because any skilled organic chemist would say that's not the expected product. Something else is going to happen. So here's what you want to look out for. Anytime you have a cation or a radical, some species that is octet deficient. Okay, a radical is one electron short of an octet. A cation is technically 2 electrons short of an octet. Anytime you have an electron deficient species, look for rearrangements. So the most common type of rearrangement is called a hydride shift, where an adjacent hydrogen will move. Now, I'm going to show you what this looks like, and then I'll explain why it happens. So in this case, this hydrogen is simply going to move. It's literally going to pack up its bags and move next door. Now think about what happens here. I'll keep with the red color here. When that hydrogen moves, the carbon that had the positive charge gets its bond back. So now this guy's got 2 hydrogens. It's got 4 bonds now. He's happy now. But the carbon that lost the hydrogen is now missing a bond. Okay? It's a rearrangement. Things have rearranged. Specifically, our cation has moved. Okay? You move the H, you also move the cation. So now, though, it's a tertiary. Okay? And tertiary is more stable than secondary. So the point is that a hydride shift like this will happen if the resulting cation is more stable than the original one. So do not shift a secondary to a secondary, or a secondary to a primary, or a primary to a primary if you're making a primary cation for some reason. Typically, you will shift a primary to a secondary, or a primary to a tertiary, or a secondary to a tertiary. Okay, so you want to look for situations where that might happen anytime that you have a cation mechanism. In this case, we have a cation and we can shift a hydrogen. So that's going to happen, and it's going to happen fairly rapidly. As long as the cation gets more stable, the shift will happen faster than nucleophilic attack will. Okay, so basically this is a race. This is a race to say who's going to get there first. Is the hydrogen going to transfer to the cation first, or is the chloride going to attack the cation first? But so the answer is that because the cation gets more stable, the hydrogen will win the race. The hydrogen is right next door. The chlorine is floating around randomly. Okay, so the hydrogen is going to shift, and we're going to get the tertiary, and that tertiary is going to stay around for a long time. So it's the tertiary cation that the chloride is ultimately going to find. Okay. I wrote bromine. It's not a bromine. It's a chlorine. Okay. So this is the actual. Okay. Results from a hydride shift. So that's what regiochemistry is. Regio means region or location. So we're just saying, like, pay attention to where the chlorine goes. Okay. The chlorine tries to follow Markovnikov's rule, but a hydride shift intercepts that, and we end up where the chlorine goes. Stereochemistry, I'm not really sure why this is being referenced here, because there's no stereochemistry here. This is not, that's not a stereocenter. You know, it's a symmetrical, this carbon has two symmetrical groups, one side of the ring and the other side of the ring. So there's no stereochemistry there. Maybe what it was referring to was this product, because this is a stereocenter. It's got the H, the methyl, the chlorine, and the ring. So that's a stereocenter, so it can be R or S. I know you and I haven't talked about R and S yet, but anyway, that could be R or S. The reason it could be R or S is because the cation is planar. And so the chlorine can add from the top, in which case it would be a wedged chlorine, right? Or it could add from the bottom, in which case it would be dashed. And that would create either the R stereocenter if it was dashed, or the S stereocenter if it was wedged. So that is maybe where stereochemistry matters, but this is a minor product. Okay, the major product will be the rearranged product. Okay. All right, moving on. We're almost done with this section, I think. Yeah. So this is where, actually we haven't done this either. So we've actually got quite a few more problems here. All right. Which of the following intermediates is thought to occur in the mechanism by which alkenes are hydrated in the presence of an acid? So we did that already. We can go back here. Didn't we? Oh, I don't remember. Anyway, let me go over that mechanism here. Alkenes are hydrated in the presence of an acid. So that would be something like this. Hydrated, right? Adding water. So in the presence of an acid, usually this is a good theory to remember. A rule of thumb, I guess, is that if you have an acid, the first step is going to be protonation. Something will get protonated. It could be a double bond or a pi bond in a double bond. It could be an alcohol. It could be a carbonyl. There's all kinds of things that could happen, but that could get protonated. But if there's acid, something will get protonated. So again, we're going to choose, in this case, we've got equal number of H's. So we can just choose one place. Let's say our H goes here. So now we've got two H's there. The other carbon ends up with a positive charge. That's our cation. Rearrangements won't help. We just end up with either a primary, which is worse, or a secondary, which is the same. So there's no reason to rearrange. But then in the hydration mechanism is where water attacks. So water is going to add to the alkene, and eventually, after we lose an H from our water, we get the alcohol. Okay. So that will, I'll say, lose H plus. We lose an H plus from our water. We get the alcohol. The point is that we make a carbocation. This is a cation mechanism. That's the following intermediate. Okay, carbanion is a negative charge. Free radical is a dot, okay, a single electron. A carbene is an interesting species. It's a carbon with two bonds and a lone pair, which is oddly, it's neutral because it's got four, two bonds and two electrons. It's neutral, but it's only got an octet. It's only got a sextet. So very weird species. It's both nucleophilic and electrophilic, right? And the alkyne is a CC triple bond. Okay, so we don't have any of those, but we do have a cation, which is a positive charge. Okay. Okay, provide the reagents necessary to complete the following transformation. So you want to look for the pattern. You want to say, what is going on here? What's the big picture? And the big picture is we're clearly using up an alkene. Okay, so the alkene is going away. We're adding an alcohol. That's fairly obvious. But we're also adding an H. Okay, so there's one H here. Right? Read your structure carefully. There's one H there. There's two H's here. So what this is a hydration. This is actually the previous reaction that we just did. We're adding an H to one carbon of the alkene, and we're adding an OH to the other carbon of the alkene. We did that before here, right? We added one H to one carbon, and then we added the OH to the other carbon. So that's what we need to do here. This is hydration. And specifically, notice the rule that we're following. The H is going on to the carbon with the most H's. So this is Markovnikov style hydration. And there are actually two ways to do this. If you learn from your book, if you go through all the alkene reactions in your book, you will learn that there are two ways to facilitate a Markovnikov hydration. And I'll show you both of them, and I'll explain why they, 5-membered ring. We'll explain why you might want one versus why you might want another. I'm just going to abbreviate this as ethyl. That's an ethyl group. So one way to do it is very straightforward. It's just acid and water. So H3O plus H2O. Okay, that will follow Markovnikov's rule. Now let me show you, I don't need to go through the mechanism because I know what Markovnikov's rule says. Markovnikov's rule says that when we do Markovnikov's hydration, or Markovnikov style hydration, the H goes onto the carbon with the most H's, which is there. The OH goes onto the other carbon. Okay. So that's it. Oops. That's one way to do it. And it's basically this mechanism. Okay. It's basically the H protonates the alkene. The H goes onto the carbon with the most H's. That leaves us with a carbocation on the other carbon. And then water attacks that carbocation. We end up losing the H from the water and we end up with the alcohol. Okay. Markovnikov hydration. The wedges in the dash here can be a little bit deceptive. This, yes, one group has to be wedged. The other group has to be dashed. But it doesn't matter which one because the ring is symmetrical on both sides. So there's not a stereocenter, no stereochem. Okay, so it doesn't matter which one. And in fact, remember the carbocation is planar. This is a planar carbon, so the water can add from the top or the bottom, either way. So don't worry about which one is wedged or which one is dashed. Just understand that one of them needs to be wedged, one of them needs to be dashed. Okay, so that's one way to do it, is just acid and water. The other way, oops. Is this. It's a little bit more complicated reagent. It's HgOAC2. So this like mercury acetate and water, followed by NaBH4. This is called oxymercuration. Demercuration. And it does the same thing. It literally achieves the same transformation. OH there. Okay. Markovnikov hydration. Okay. Same idea. But it does it by a very different mechanism, as you probably guessed. And specifically, there are no carbocations in this mechanism, which means that you can't have rearrangements. If you use oxymercuration, demercuration, rearrangements are not an option. They are not available. They will not happen. If you use hydration, if you use this acid catalyzed hydration, then you do get cations. Okay. And so you have to look out for rearrangements. Could rearrange. So you have to ask yourself when you're doing these types of problems, if I use the acid-based mechanism, will it rearrange? And do I want that rearrangement? Because maybe you do. Maybe you want the hydration and the rearrangement. In that case, use acid and water. If it can rearrange, but you don't want that rearrangement to happen, then you have to use oxymercuration, demercuration. If no rearrangements will happen, then it doesn't matter which one you use. So in this case, let me show you why it doesn't really matter. Because the site at which we will create the cation, let me go down here and kind of sketch out the hydration mechanism. So remember, we've got acid. The pi bond is going to grab the H. It's going to put the H on the carbon with the most H's, following Markovnikov's rule, which means that the H goes there. We've got our ethyl group, and our carbocation is here. That's already tertiary. There is no neighboring hydrogen that could shift and result in a better cation. Okay, this ethyl group, I've been abbreviating it for simplicity, but okay, that ethyl group has 2 hydrogens. The ring carbon next to it over here has 2 hydrogens, and the ring carbon down here has 2 hydrogens. So imagine if one of these H's moved over, we'd end up with a secondary over there. If one of these H's moved over, we'd end up with a secondary. If one of these H's moved over, we'd end up with a secondary. So there's no reason for a shift to occur. And so it won't. And therefore, we don't have to really worry about a shift. We want the OH in the position where it's already extremely likely or basically guaranteed to end up. Okay. So maybe, I'm not sure, maybe your professor would prefer you to use one of these. When I teach it that on paper, either is fine, but you have to pay attention to rearrangements. Okay. Again, if you want rearrangements, or if the product you want relies on a rearrangement occurring, your only option is the acid-base mechanism. If your product relies on a rearrangement not occurring, when it could occur, you need the oxymercuration mechanism. If reactions are not likely to occur at all, then it doesn't matter which one you use. Okay. The mechanism for oxymercuration, demercuration is, it's not too difficult. It's kind of long and not super important. So look it up in your book, because literally if I were to draw a mechanism, it would just literally be repeating the mechanism in your book. So go look that up. It involves making a 3-membered ring with a mercury called a mercurinium ion, and then opening the mercurinium ion with the water. All right, but everything we've talked about with mechanisms, you should understand from it. Okay, we're almost done. Treatment of alkene with an alcohol in the presence of an acid catalyst produces the ether. Provide a mechanism. All right, so this is very similar to what we saw with the HBr mechanism. Okay, you can learn it as a separate mechanism, like in your head or in your flashcards. You can study it as a separate mechanism if you want, or you can logically group it with HBr because it works the same way. Okay, here's our starting material. And like I said before, anytime you have acid, your first step should be a protonation. So the pi bond is going to protonate from the acid. And we're going to follow Markovnikov's rule. Remember, the only time we violated Markovnikov's rule was when we were dealing with that free radical mechanism. Any of these cation-based mechanisms where we've got acids, positive charges, they all follow Markovnikov's rule. In your book, as you're studying these, your book will, go through each mechanism and it will specify, it'll remind you, it'll say, this is Markovnikov, this is anti-Markovnikov, okay, whatever. All right, so we're going to, again, analyze this. Which carbon does the H go on? The carbon goes on the H, or the H goes on the carbon that has the most H's, which is this one. This carbon has an H on it. So we're going to put the H there. Which will give us a tertiary carbocation, right? Awesome. That's great. Okay. Because it means it's not going to rearrange. You don't have to look for rearrangements. It's tertiary. Okay. Now in the HBr mechanism, remember the Br minus attacked. But we don't have Br minus here. So what is going to attack is the alcohol. So this is HOCH3. That's methanol. And the O is going to attack the tertiary carbocation. So we have now on that carbon, we have the OCH3. It's still got the H on the O. Don't forget about that H. It's important because that's going to give the O a positive charge. It's got the O is 3 bonds now. And then we've got our methyl there. And then in the last step, another methanol probably, another HOCH3. Can grab the H and return those electrons back to the O. There we go. All right. So, again, that's acid and alcohol. You could think of it as, being essentially the same mechanism as HBr. It follows Markovnikov's rule, protonate the alkene, make the carbocation, add the nucleophile. The only real difference is that since our nucleophile since our nucleophile is neutral, once we make a new bond to it, we have to lose an existing bond, which will be the H. With HBr, the nucleophile was bromide, Br minus. So once we made the new bond, it was already neutral then. So there's that one extra step where the deprotonation occurs. That's different from our HBr mechanism. But that's that. This is classic electrophilic addition. Okay. All right, 30. Provide the reagents necessary to complete the transformation. Okay. So look at what's going on here. We've got an alkane. Remember the other day we said you can't really do anything to an alkane except free radical halogenation. That was our bootstrap. We're going to take something with no functionality and we're going to add functionality. Once we do that, then we have to worry about getting the OH on there. So let's start with our plain non-functional alkane. The free radical mechanism was, or the free radical reagents were Br2 and light. And remember, in this reaction, the halogen goes on the most substituted position because it's going to make a radical, and that radical is going to be formed at the position that can most easily deal with being electron deficient. That's our tertiary site. So that's going to create the tertiary radical. And that's where the bromine ends up. Okay. So that, interestingly, maps pretty nicely onto our product. Great. Looking at this, my thought process when I saw this was, okay, we want the OH to end up on the position which is the most likely position to receive a radical or to receive the halogen when we do the free radical halogenation, which is pretty much the only thing we can do from an alkane. Okay, now there's two pathways that you might take from here, and I'm going to show you both of them. You could do an elimination. So do something like KOH and heat. Do a dehydrohalogenation. Do a Zaitsev style elimination. Because now notice that our position where we want the alcohol is the Markovnikov position. If we do a Markovnikov hydration of this, the alcohol will end up exactly where we want. Like that. So we'll do something like H3O plus and water. Or, I'll say, or the oxymercuration, demercuration, right? Because it's Markovnikov hydration. And in this case, we want the alcohol at the tertiary site. And that's where the carbocation will be without any rearrangements. So we don't have to worry about rearrangements. We can just use hydration. But we also could do oxymercuration, demercuration, because that would give us the right pattern too. So here the OH goes on the more substituted carbon, the H goes on the less substituted carbon, or the H with the most H's, which is this carbon here. So that's one way to do it. You could also do an SN1 reaction, which, given the context of this problem, I'm thinking is maybe not what was intended, but you could use H2O and AgNO3. AgNO3 is one of those ionizing solvents. And this would do a substitution. Where the water displaces the bromine and will eventually lose the H off of the water. So this is an SN1. That's another way to do it. Both are fine. Generally you want to use as few steps as possible, because every time you do more steps, it costs more chemicals basically, and you increase the risk of losing product somehow. So fewer steps is better, but, you know, doesn't really matter on paper. All right. So learn the patterns, right? Learn which reaction is associated with certain patterns so that when you see those patterns, you can recall those reactions. You also want to think of these things as being interconnected, right? In this case, you know, we needed 2 or 3 steps. And if you don't study how the reactants of one, or how the product of one reaction could act as a reactant for another, you're not going to see how they interconnect. So you want to think about them as being related in some way. We can take an alkane, make it into a halogen, make it into a double bond, make it into an alcohol, or take the halogen, substitute it to the alcohol, right? You can, you know, these things interconvert. We could also do a dehydration, take the alcohol, dehydrate it, and then rehydrate it if we wanted to. That'd be silly. But that's the idea. Learn how they are interconnected. All right. Now, here's a big picture problem, because they're asking not for the mechanism, but for the overall product. And here are oxymercuration, demercuration. Okay. We know this, that your brain goes, wait, I know what this does. What does it do? Markovnikov hydration. Okay. So Markovnikov's rule, okay? Markovnikov's rule says we add the H onto the carbon with the most H's. So we've got 2 H's here. We've got 1 H here. Okay. And so if we apply the pattern, we'll put the OH here and the H there. That is it. Okay. That is your product. Now, here's the thing. If we had done the hydration, the acid catalyzed hydration, we would have ended up with a cation here, right? Our first step would have involved protonating the double bond, generating a cation here. And just like we said, a hydride can shift, what also can shift are methyls. And we've got 3 of them right next door. So notice that this is a secondary cation. And if we move a methyl over, like that, the carbon on the right has now lost its bond. And so that's tertiary, right? And so we'd end up with a different product at the end of the day. We'd end up with the alcohol at that site. If we had done hydration, if we use H3O plus and H2O, we would have had to worry about that rearrangement. Okay, but because we didn't, because we used the oxymercuration, demercuration, which with no rearrangements. We can just go straight to the product. So this is a perfect example where if you want this product, you have to use these reagents. Okay, it says pay attention to regio and stereochemical detail. We have done that. We have fully vetted that this is going to follow Markovnikov's rule with no rearrangement. So we know exactly where the OH is going to go. This is also a stereocenter. We've got the bond to the O. We've got the OH. We've got a bond to a methyl. We've got a bond to the T-butyl group. And we've got an H. So we've got 4 different groups. So we have stereochemistry, and this can be R or S. Okay, meaning that the OH can be wedged, in which case it would be R, or it could be dashed, in which case it would be S. Okay. Now let me double check your answer key to make sure that you did, in fact, do no rearrangements, because there should be no rearrangements here. Good. Yeah, no rearrangements. Okay. So this is, in fact, what's on your answer key. Your answer key does go through the mechanism, which is great, because I told you to look that up. It goes through the mechanism for oxymercuration, demercuration, and you end up with the alcohol exactly where you'd expect. Okay. Now the next question is kind of related to this. In this reaction, we use H2O. And it's that water that ends up being the alcohol. Okay. There's a modified version of this where you use an alkene with HgOAC2, this diacetyl mercury, followed by, or in alcohol though. Okay, so this is ROH. Okay, not HOH, not water. Okay. Instead of getting the OH in the alcohol, you get OR. So something like this, your alkene, under these conditions, you get Markovnikov OR. Okay. That's called alkoxymercuration. That's called alkoxymercuration. Works the exact same way, pretty much the exact same mechanism, but instead of water attacking the mercury, that mercurinium ring, it's an alcohol that does it. And so you end up with OR here. And what this is asking, what class of compound do we make? It's an ether. It's a carbon connected to an oxygen connected to a carbon in the R group. So it's ROR, where we're adding the OR group. Okay, so that's an ether. That's called alkoxymercuration. If instead we use water, then it's what we just did. Then it was the alkene. Oops. To make OH. And that's an alcohol. All right. So that is it. We already did 34 and the rest of the problems during our lesson. So I'm going to cut here, and then we're going to switch over to the Wade problems. Okay, so the problems from Wade. It was 761C. Let me get at my list here. So 761C, propose mechanisms for the following reactions. Additional products may be formed, but your mechanism only needs to explain the products shown. Okay, so they actually do give us the 3 products for C. This is a little bit different from what we saw, where we used an alcohol and we also added acid. Okay. In our previous problems, we had acid here. But in this case, they're not giving us acid, but we can kind of imagine as if we did. Notice that the location where the OET ends up is different in a couple of cases, and we also have a double bond. So first of all, notice that we've got a substitution and we've got elimination. And since the nucleophile is adding at different sites, that means that we've got either resonance or rearrangements. We need some mechanism by which a cation can move. Otherwise, there's no reason to explain how the nucleophile can add to these different positions. So let's go through this. I think probably the easiest place to start is to actually recognize what our reagents are saying. Okay, neutral nucleophile means SN1. Heat with a neutral nucleophile means E1. Okay, so we've got those 2 mechanisms. Both of them, both E1 and SN1, involve the halogen leaving on its own. That gets us a cation with the double bond. Now, to get to our first product, it's very straightforward. Our HOET simply adds to the cation. We've got our double bond in the same place. We have the OET. We've still got the H on it, so we've got a positive charge. But then the bromide, which we kicked off previously, can come in and grab the H, return the electrons to the O, and we've got OET. Okay. That's our first product. Our second product is also going to be an SN1. I'm going to duplicate this because this gets us to kind of a deviation point. or our mechanism can branch. Because we've got resonance, we can take this pi bond and it can move. It can move because there's an empty spot for it on the neighboring carbon. Electrons don't like to be pinned down. They don't like to stay in one spot. So if they can move, if they can spread out, they will. And there's an adjacent empty valence next to that pi bond so it can move. So when that pi bond moves, so does the cation. And notice that that's exactly where our OET needs, hang on one sec. All right, sorry about that. That's exactly where our OET needs to be in the second product. So we can have our HOET, our SN1 type nucleophile is going to add. Let me erase that. Where our double bond is here, we've got HOET with the positive charge, just like before. And then our bromide can come grab the H. And we get to our product. Right, that was what we had here. Okay, notice that the double bond moved. That's a sign. Right, we've got resonance. Okay, the second or the third product, notice our double bond is also there. But instead of having a substitution where the nucleophile adds to the cation, we've done an elimination. Yeah, actually I misidentified this double bond here. It's this double bond that's the elimination. Okay, so it's the same setup. The mechanism is going to proceed exactly the same way up until that nucleophilic attack. So I'll duplicate this again just so you can see it. Leaving group leaves, we get resonance. Carbocation is delocalized. That's good because it means it's spread out. Then we've got a hydrogen right here, which our HOET can remove. Okay. So that is going to grab the H. The electrons fall in, and we make a pi bond. So that's kind of the beauty, but also the complexity of the E1 and SN1 mechanisms. Because they go through cations, you can have rearrangements, you can have a resonance, which moves that charge around. And when you move the charge around, you therefore will also move where the nucleophile ends up if you're doing a substitution, or you can move around where the double bond ends up if you're doing elimination. So anytime you see those deviations in structure where things are moving around, think about E1, SN1 with resonance or cation shifts. Okay. This is a bit ridiculous. This is pretty much every problem in, or every alkene reaction in the chapter. I will go through and write the answers to these things. I'm not going to do the mechanisms. They want you to give the product of the reactions and give the structures of intermediates. So this requires you write out every single mechanism. include stereochemistry where appropriate. It's just an insane amount of time that I honestly don't have. And we've talked about these reactions already. So you can reference those mechanisms if you want. The point is to take the reaction, look at the reactants, the starting material and the reactants, decide what kind of reaction it is, recall what the pattern is, and then apply that pattern to our structure. Okay, so alkene plus HCl, this is Markovnikov halogenation. We're adding HCl across the double bond. I'm going to put a little M here for Markovnikov. What that means, apply our pattern. The H goes onto the carbon with the most H's. Oops, I did that wrong here. The H goes onto the carbon with the most H's, which is here. The chlorine goes on to the more substituted carbon. Okay, there's your Markovnikov addition. All right, Br2, CCl4 is the solvent. Br2 adds the bromines across the double bond. So we have a bromine on one side of the double bond and the other side of the double bond. And remember, that mechanism makes that bromonium ring, which can be wedged or dashed. And then the bromide pops that bromonium ring open, and you end up with anti-bromine. So one of these would be wedged, the other one would be dashed. Okay, and both combinations are possible. So that means that we have an enantiomer plus ENT. So both combinations of wedges and dashes. Okay, this reaction, we actually haven't done it together yet. I'm going to draw it right here. But this is anti-Markovnikov. H and OH. And specifically, it goes syn. Meaning that the OH and the H add to the same face. So if I analyze this, this is the anti-Markovnikov position. That's where our OH will go if we violate Markovnikov's rule. So let me draw this down here, actually. There's our alkene. We're going to put the OH at the anti-Markovnikov position, which is there. Okay. The H goes onto the carbon with the fewer H's, right there. And the H and the OH are always syn. So that means that if the OH is wedged, the H is wedged, which means that the methyl will be dashed. Okay, so that's that product. That's called hydroboration oxidation. So the first step is hydroboration. The second step is oxidation. If you look in the book for the mechanism, the BH3 adds the boron and the H simultaneously. So they add to the same face of the alkene. And then the second step, the oxidation, converts the boron into an O. So the OH ends up on the same face as the H. Okay. D. So D is called ozonolysis. I'll draw that down here. Okay, so what ozonolysis does is it cleaves an alkene. It literally snaps the molecule into two pieces. Okay, not literally. It figuratively snaps the molecule into two pieces. It does it by a very interesting mechanism that is probably not even in the book. But the point is that if you split those two pieces, you patch them with a double bond O. Okay, so over here, we've got, I'll use blue. We've got the two blue carbons, which end up here, where the carbon that was involved in with the double bond ends up with the double bond O. This H was here to begin with. It was there in the first place, right there. The other side, the yellows, four carbons, 1, 2, 3, 4. And the carbon that was involved in the double bond ends up with the double bond O. That is ozonolysis. It's called oxidative cleavage. Cleaves the double bond. Okay. You end up with aldehydes and ketones. Aldehydes, if one of your sides has an H on it, like here, you get an aldehyde. If it doesn't, if you only have carbons, it's a ketone. So you can get any combination, 2 aldehydes, 2 ketones, aldehyde and ketone. They can be the same, they can be different, depends on your starting material. But the point is that it cleaves the triple bond, or it cleaves the double bond. Okay, next reaction, we've seen this. HBr, ROOR, right? That was anti-Markovnikov, right? So the product will use up the single bond. Let me erase this here. I need more room. We'll use up the pi bond. The bromine goes in the anti-Markovnikov position. Right? So again, this is we've got 2 sites. Normally, the H goes onto the carbon with the most H's, but with anti-Markovnikov, the H is going to go onto the carbon with the fewest H's, and instead the bromine is going to go onto the carbon with the most H's, or with the most H's. So that's our product. That's the anti-Markovnikov product. Now here's a mean little trick. It doesn't work with HCl. You don't get the anti-Markovnikov pattern with HCl. You still get Markovnikov. Oops. Okay. So that's a mean trick. It's basically the chlorine radical is too reactive, and so it jumps right where it wants to be instead of being patient like the bromine is. Okay, so this is not anti-Markovnikov, and that should be covered in your text, in the textbook. All right, here's that weird acid again, the CO3H. That is a peroxy acid. And that makes that peroxide, or excuse me, that epoxide. So between the carbons, that are involved in the double bond, we're going to bridge an oxygen. Okay. And those wedges can be both wedged or dashed. So plus an enantiomer. Okay. OSO4 and H2O2. We've seen this. This was SN diols. Right? Learn the pattern. So the pattern is that the OHs go SN. We add OHs to both carbons. They're both wedged or both dashed. That's going to, in this case, if they're wedged, that's going to put the methyl group down. Plus an enantiomer. Okay. All right, so that's the OSO4. KMNO4, cold. So this is kind of interesting. KMNO4 will do a lot of different things depending on the conditions. So for example, here's KMNO4 cold. Here's KMNO4 warm concentrated. They do different things. KMNO4 cold does the same thing as OSO4. So SN diols. In this case, that's going to push the methyl group down because I put the OHs up. You could also flip the wedges and the dashes and get the enantiomer. Okay. So SN diols from either OSO4 with H2O2 or KMNO4 cold. All right, the next one, this actually should be one step, two step. Come on, Wade, get it straight. All right, so the first step, here's our peroxy acid, right? The CO3H, just like before. So remember what that's going to do. That's going to make the epoxide. Oops. That's going to make the epoxide. It's going to make the epoxide across our triple bond. It's going to use up the triple bond, right? But then the water and acid is going to pop that open. And so we get anti-diols. So we're going to have diols, but they're going to be opposite. And in this case, if I put the OH up, then the methyl on that carbon has to go down. But we could flip everything around and also make the enantiomer. So switch the dashes and wedges. Okay, so that's anti-diols. All right. KMNO4 warm is a lot like ozonolysis. It does a very similar reaction, except that wherever you would have aldehydes, like we had here, wherever you would have aldehydes, you end up with carboxylic acids. So let me draw that. So all right, so we've got our 6-membered ring with the methyl. Like that. We're going to cleave our double bond. Okay. And wherever we would have an aldehyde, like we have here, there's an H there, we're going to convert that H into an OH. So what I like to do is draw everything in place, but leave out the double bond. And then over here, put the double bond O. And then over here, we have the double bond O with the OH. Okay. So you cleave the double bond, replace, okay, on those carbons, the carbon that had the double bond on one side and the carbon on the other side that had the double bond, their bonds get replaced by the double bond O. But if there's an aldehyde with KMnO4, that H gets converted to an OH. So it's a carboxylic acid. That's KMnO4 hot. Okay. They give us another ozonolysis reaction here, which is, notice it's the same starting material. It's the ring, same ring. So whereas with KMnO4, we converted that green H there into an OH. With ozonolysis, we're going to cleave it the exact same way, but we're going to leave that green H there. Okay. If you wanted to, you could draw this out like in a, we've got 1, 2, 3, 4, 5, 6, 7. So it's 7 carbon chain. 1, 2, 3, 4, 5, 6, 7. On carbon 2 is the carbonyl. That's a ketone. Here on carbon 7, it's an aldehyde. In the other molecule, 1, 2, 3, 4, 5, 6, 7, we have the ketone in the same place, but the aldehyde gets converted to a carboxylic acid. So that's the ozonolysis version of that. Just have to ask yourself, what do you want? If you want the aldehyde, you need ozonolysis. Okay. Next reaction, very deceptively tricky reaction. I say it's deceptively tricky because we learned that H2 and platinum will convert the double bond into a single bond, or basically convert the pi bond into 2 new sigma bonds. So something like this. Where we're going to just essentially, you can think of it as just getting rid of the double bond like that. But it's a little bit more complicated because the H's add sin. So notice that there are no H's on these double bonded carbons. But when we get rid of that double bond, we are putting H's in. And what you have to remember is that in hydrogenation, the H's add sin. Okay, so if those H's add together so that they're wedged, or together so that they're dashed, that's going to make the methyl groups the opposite. Okay, let me redraw this a little bit nicer. So we have to have the H's together. So maybe we do this. Maybe we make the methyl groups wedged. And then the H's add dashed. Okay. So there is important stereochemistry. Okay. The methyls have to be together. You can't just plop the H's down and forget about it. Okay, they do add sin with H2 and platinum. Or I think they used palladium here. Oh no, it was platinum. All right, a few more. H2, H plus and H2O, that's Markovnikov hydration. We did that, so the Markovnikov position for the OH is there. And the H goes on the carbon with the most H's. Okay, so we use up the double bond is gone. You know, maybe we do this. Yep, double bond's gone. Okay, so that's Markovnikov hydration. Notice that the Markovnikov carbon, the carbon that gets the OH, is already tertiary. That's tertiary, so no rearrangements are going to happen. We're not going to be moving any H's around. We're already at a tertiary location. Okay, this is called ring closing metathesis. It's not a reaction that I teach very often. I don't know how much time the book spends on it, but basically, this catalyst, this is a metal. It's usually a ruthenium catalyst. Causes the ring to close with a double bond. So these two double bonds kind of combine. They both get used up. And the ring closes with a double bond. Okay. It's kind of a cool mechanism. I don't know if the book shows it, but it's kind of a cool mechanism. I think it got the Nobel Prize back in 2004, maybe 2005. Something around there. It got the Nobel Prize. Okay. Here's our oxymercuration demercuration. We talked about alkoxymercuration demercuration. So we are aware that there is a variation where an alcohol would be used here instead of water. But this is also Markovnikov hydration. And so you get the same product, the OH there, the H there, and the pi bond gets used up. Okay. And then finally, Cl2 and H2O. This is like the Br2 reaction here, where we make that bromonium ring and then pop it open, and we end up with the trans or the anti-bromines. In your practice sheet, in your practice problems, you did a reaction where we made the bromonium ring, but then we attacked it with an alcohol. And that's actually what happens here is the water pops open the ring instead of the chloride. So this looks like this. They happen to give us two rings. That's okay. We'll make the chloronium ring. So we'll make this like three-membered chlorine ring. But it's going to get opened by the alcohol. Did I put the double bond in the right place? I think I might not have. I didn't. I put the double bond in the wrong place. So I knew that because this is an interesting feature of this reaction. So if the double bond is there, the chloronium ring is going to form there, involving those two carbons. And what happens is when the alcohol pops it open, remember how we attacked the more substituted carbon in that problem? If you go back and review our work, the alcohol added to the more substituted carbon to pop open the ring. So the water does the same thing here. We said anytime you have a three-membered ring with a positive charge, that ring gets opened from the more substituted side. So what you end up with is the OH on the more substituted carbon. And let's make that, let's make it dashed. I should have done that. So since we drew the chloronium ring up, we made these wedges here. The OH is going to add from the back. The water is going to add from the bottom. The bottom of the more substituted side, if you make the chloronium ring up. It'll attack from the top of the more substituted side if you make the chloronium ring down. So you get this anti-H and halogen. That's called hydro. I forget what it's called. I'm blanking. I want to say it's hydrohalogenation, but that's a halohydrin is what it's called. It's called a halohydrin. Okay, and that's how the halohydrin reaction works. So plus an antimer. Okay, because the OH and the OH and the Cl could be opposite, wedge versus dash, dash versus wedge, if the original chloronium is dashed instead of wedged. But always the OH on the more substituted carbon. So think about it as the OH is Markovnikov. The chlorine is anti-Markovnikov. Okay, our original positions, Markovnikov, anti-Markovnikov. Okay. Okay, this is the same. This is the same type of stuff. I'm gonna skip this. It's the same reactions. The only thing is you have to pay attention because we've got two double bonds here. We've got the double bond here and the double bond here. So here's the logic. This double bond is more electron rich. This double bond is electron poor. Okay, actually, now that I'm reading the prompt. Okay, so here's my thought. Because one of these is electron rich and one of these is electron poor, one would react in preference to the other, depending upon what the reagent is. If the reagent is electron poor, then this alkene would react. So if the alkene is acting as a nucleophile, this is our side that reacts. If the reactant is acting as an electrophile, this is the side that reacts. But now that I read this, it says an excess of each reagent, which means I think they're asking for both of them to react. So I think you're gonna do whatever you do to both of them. Okay. But all of these reactions are ones we've covered before. Okay. This borane and tetrahydrofuran, this was the BH3 THF reaction, which was anti-Markovnikov hydration. MCPB8 was epoxide formation. Ozone, cleaving the double bonds and leaving aldehydes. Osmic acid, okay, that's OSO4, and hydrogen peroxide, that was syn-diols. Hot, concentrated KMNO4, cleaving the double bonds and turning aldehydes into carboxylic acids. Peroxy acid, making the epoxide and then opening it up to make antidiols. Hydrogen in a platinum catalyst. Hydrogenation, where the H's add syn. Hydrogen bromide gas, HBr. That's Markovnikov addition of HBr. Okay. Hydrogen bromide gas in a solution containing dimethyl peroxide. That was anti-Markovnikov, HBr. Bromine water is Br2. It's confusing because there's no water. I think that's what they mean by bromine water. It's just actually, I think that's Br2 and H2O, which is basically what we did here. This was Cl2 and H2O. I think that's what they mean by bromine water. Chlorine gas, just Cl2. That was like just Br2. So up here, we did Br2 and CCl4. Okay. Same thing with Cl2. Mercuric acetate in methanol. Okay, not in water, in an alcohol, followed by sodium borohydride. So that was alkoxymercuration, demercuration. Okay, where you're adding Markovnikov OR. Okay, and then CH3Br and 50% aqueous NaOH. What's that doing? To be honest, I don't recognize that. Oh, carbene. This makes a carbene. So CHBr3 will get deprotonated to make CBr3 minus, which will dissociate into this carbene. And what this does, let me just show you that because we haven't seen that yet. If you take an alkene and you add this carbene to it, it's going to make a 3-membered ring with the carbon that ends up with the 2 Brs on it. So this carbon with the 2 Brs is this carbon with the 2 Brs. But the carbene is extremely reactive, and you can't just put it in a bottle. So you have to make it kind of in your flask. So you start with CHBr3, you use the NaOH to remove that H, and you end up with CBr3 minus, where the negative charge is on the carbon. And then one of the bromines falls off and leaves its electrons behind. Oops. Leaves its electrons behind on the carbon. All right, so that's carbene formation. But okay, every one of these reactions we've seen before. Okay, and what I just did, what I listed off, is what the big picture is, right? anti-Markovnikov hydration, Markovnikov hydration, anti-Markovnikov BR, anti-Markovnikov, or Markovnikov BR, whatever, cleaving a double bond and leaving aldehydes, cleaving a double bond and losing carboxylic acids. You want to learn what each set of, maybe you think of it as a recipe. Learn what each recipe does. Learn its pattern, and then you just apply it to your structure. Okay. Same idea here. It says, how would you make the following compounds from a suitable alkene? So they're asking us to start from a cyclic alkene. And we want to make this. So you can ask yourself, what pattern do we want? Or what do we have on our product? For example, antidiols. Okay, we'll go through each of these, but antidiol, syndiol, synbromines, OHCl. We've just got a plain old OH and an OCH3. Okay. So every one of these patterns has shown up in a reaction that we've learned already. For example, we learned how to make antidiols. How do we make antidiols? We do it by making an epoxide and then opening that three-membered ring under acidic conditions. So to get there, let's start with our cyclic alkene as per our requirements. The two carbons that are involved in the antidiols need to be the carbons that are involved in the double bond. We also need a methyl group there, so let's make sure we include our methyl group. So our first step is going to be MCPBA. That's going to make our epoxide. And then we're going to pop it open with H3O plus. So we'll have our methyl, and here they made the methyl wedged. That's just because they chose to make this OH dashed. But it doesn't matter because both can happen. The OHs just have to be anti. Okay, syndiols. We saw two ways to do this, with OSO4 and H2O2 or KMNO4 cold. Okay, so for the second one, they use an 8-membered ring. That's a bit of a pain. But there's our double bond. We're going to use OSO4 and H2O2. And we get the syn diols. Okay, third one. I'm just going to treat this as a 6-membered ring. I'm not going to bother drawing all 10 carbons. But the point is that if we want, was that syn BRs? We not done syn BRs, have we? I'm curious. Let me check the key, because I'm not sure if maybe they want 2 steps. Maybe they want 2 steps. Let me check. I was thinking anti-BRs. This is 849. Oh, I see. This is super tricky. So, so this is actually quite tricky. So look at this. If you have a a cis double bond, and you use Br2, just Br2. You will get the anti-bromines. Okay, this is anti. Okay. So if we want, and this is why they actually use the 10-membered ring. If you want syn, you actually have to start from a trans double bond. Well, it looks weird because the way that the product is drawn, it looks like we have to put the double bond there, but this is a ring. And we can put the double bond anywhere around the ring that we want. So since we know that we want the BRs to add opposite of how they normally would, we want to put the double bond in the trans position. Okay. The idea is this. Look, if I start with a trans double bond and I use Br2, those bromines can perfectly well add like this and opposite like this. Okay, but if I rotate this single bond, then the molecule looks like this. Okay. So it looks like we added syn. But it really didn't because we've rotated our bond around. Okay, we really added anti. Okay. So here, remember the bromines always add anti. But in order to make them look syn, we have to start from a trans double bond and then imagine the molecule like transposing itself so that our bromines look like this. So something like this, the idea is that if we add the Br2, it's going to add anti across that double bond, just like you'd expect. Okay, it's not a different reaction. We're going to add anti across the double bond. But then in order to make the molecule look that way, we have to have it transposed. We have to have the ring flip, basically. And the ring can only do that if it's a big floppy ring like this. So that's a very, very tricky problem. I probably wouldn't worry about that one. All right, anti-OH and Cl, that was where we started with our alkene. We use Cl2 and H2O. That makes the chloronium ring. And then the water opens that up. So the water would be on the back side, or the OH would be on the back side, and then the chlorine would be on the front side. That's only because we made the chloronium wedged. If you made the chloronium dashed, you get the other configuration. Okay, now these are kind of fun because we have a lot of options. Okay, notice where the OH is on that ring. So here are a couple options that we can pursue. And I'll explain why one is better than the other. If we start with our double bond here, okay, we specifically want the OH there, okay, which is anti-Markovnikov. That's the position that would be violating Markovnikov's rule. Okay, so we could use BH3THF. Followed by NaOH, H2O2. And the OH would go here, and the H would go there. That's exactly what we want. Let me show you why there's another option that might look tempting, but is not. You might imagine starting with the double bond there. The problem is that if you start with the double bond there, these are equal. These carbons have the same number of H's. So there's no Markovnikov or anti-Markovnikov aspect to that, which means we can't control which carbon the OH or the H would go on to. And what that means is we have a 50-50 chance of getting it where we want, but a 50-50 chance of it going where we don't want. Whereas if we start with an asymmetrical alkene, we have full control over adding to one side of it. In this case, we want the anti-Markovnikov pattern. And so we use the anti-Markovnikov reagents, BH3THF, followed by NaOH and H2O2. Okay. And then last one maybe. Okay, that was that. So over here, we want to add an OCH3. Notice that that's a Markovnikov position. Okay, if we have the double bond here, that's the Markovnikov position. If we have the double bond here, it's the Markovnikov position. Okay, if we have the double bond here, come on, here, then it's not. Now we've got a symmetrical double bond. See that? So that's not the place that we want our double bond to start. We want to start with an asymmetrical double bond so that we have control over where it goes. So we have control over what side reacts. So we'd probably start like this. Put the double bond there. And then do something like H plus and HOCH3, just like we did in the practice problem. On the other sheet where we used acid, this was where I said like HBr. We do Markovnikov addition of an H and the OCH3. All right. Okay, using 1,2-dimethyl cyclohexene, which is this guy. Show how you would synthesize the following compounds. It says once you've synthesized a compound, you may use it as a starting material in other later parts. So what they're going to do is they're going to ask us to make this they're going to make us do this basically. And then we're going to convert this into this. Okay. And then we maybe convert this into this, right? They're going to ask us to do all kinds of different conversions here. All right, how are we doing here? What are we looking at? So after this, we got one more. All right. So let's start. The first thing, again, we have not done this together. But this position next to a double bond is called the allylic position. Now, that's allylic. This is allylic. This is allylic. And this is allylic. Okay, they're all allylic. These are secondary. That one and that one. These are primary. That one and that one. And it turns out that in a free radical halogenation with Br2 and light, the allylic positions are favored. So that's exactly what we want in this first step. If we use Br2 and light, we will halogenate at a secondary allylic position. Notice that if we halogenate down here, it's the same product. It's a symmetrical starting material. So Br2 and light is what we need to brominate an allylic position. Then what we can do is we can substitute. We can use something like NaOH or water or both. We'll substitute. either by SN1 or SN2. Just a simple displacement. All right. Looking here, what do we have? Anti-bromides, anti-dibromides. So we can go from our starting material to C using Br2 and CCl4 as our solvent. All right, Br2, CCl4, just anti-bromides. What do we have here? Again, pattern recognition, right? OH, OH, syn. How do we get syn diols? From our starting material, either OSO4 and H2O2, or you can use KMNO4 cold. Would also do that. So syn diols. Anti-diols. OH up or OH down, OH up. We've already done that. Anti-diols. First, you make the epoxide. With something like MCPBA, our peroxy acid, and then we open it up under acidic conditions, H2O and H+. Right? So anti-diols. Interesting. What do we do for this? Let me check the answer key. I wonder what they're thinking of here. Oh, okay. So what they want to do here is start from the two halogens, start from the two bromines. So start from this guy right here. And then do a double elimination. Okay. So two eliminations like KOTBU. Big bulky base, remove it from the actually KOTBU is not what you want to use here. You can use NaOH because we want to eliminate from the Zaitsev side. We've also got these methyl groups here, so that could be Hoffman. We don't want to eliminate from the Hoffman side. We want to do Zaitsev. All right. So here we have anti-OH and Br2. Or, yeah, anti-OH and Br. So we've done that as well. Where we take our double bond. We use Br2 to make the bromonium, and then we open it up with water. So we get the OH and the Br anti to each other. Right, we did that before. Here, we did it with Cl2 here. Now we're doing it with Br2 here. Again, recognize the patterns. Okay. H is not obvious. So we're making a double bond. Ah, we can make it from G, can't we? We can take this and eliminate it. It's a little bit suspect because we have to kind of hope that our alcohol doesn't do anything. But you can use something like KOH and heat. By using KOH, you get the Zaitsev elimination, and you're not using acidic conditions, so you're not really at risk of dehydrating the alcohol. So using base here, a nice small Zaitsev base is a good idea here. KOH and heat, that'll eliminate. Again, take this H from one of these Br, or take these H from a next to the Br, electrons come down and push off the bromine. All right, and then here notice that it's a 1, 2, 3, 4, 5. It's a 6-carbon chain, and we've got these ketones. So essentially all we've done is we've taken our starting material and we've cleaved that double bond in half. And since we don't have any aldehydes, we don't have to worry about whether it's ozonolysis, which would retain the aldehydes, or KMNO4 hot, which would convert the aldehydes into carboxylic acids. So we can do that from our starting material. Let's just use ozonolysis, O3, and then DMS. All right. These are not necessarily easy. They might take you a few minutes to think about, but again, the point is that once you learn the reactions, you know you've got them cataloged in your head or on a cheat sheet of some kind, in your flashcards, however it might be. Once you've got them cataloged in such a way that you can relate the reaction to the conversion, what you have to start with, what you are finishing with, what the pattern looks like, then you're just doing pattern recognition. Okay. And recall, right? I look at this, I go, oh, look, a 6-carbon chain that's got 2 ketones on it. That certainly looks like it could have been a ring that had been cleaved open using ozonolysis. Okay. Okay. Last one. Show how you would make these from methylene cyclohexane, which is this guy, as your starting material. So same idea. Let's do pattern recognition. Okay. And then once we recognize the pattern, then we have to just remember what conditions make that happen. So here, again, this is our focus. This double bond is our focus. It's an asymmetrical double bond, which means that one side, the less substituted side, I think of that as the anti-Markovnikov side. The more substituted side, I think of as the Markovnikov side. Okay, so what are we doing here? We're adding an OH, Markovnikov. Okay, or we'll put it this way. OH to the more substituted side, and then an H. Remember, there are 2 H's here to begin with. We're adding a third H here. So the H goes on the carbon with the most H's. That's Markovnikov's rule, right? The OH ends up at the position where we'd expect for Markovnikov. So Markovnikov hydration, we could do that with oxymercuration, demercuration, or H3O plus and H2O. Okay. Markovnikov OH. Okay. All right, over here, what are we doing? We're adding the bromine to the less substituted side. And we're adding an H to the more substituted side. So we're adding an H to the carbon with the fewest H's. That's anti-Markovnikov. So how do we add anti-Markovnikov H and Br? That was with HBr and ROOR. That radical mechanism we went over. Okay. All right. Same thing over here. We're adding an OH to that side and an H to the more substituted side. So that is anti-Markovnikov. And we saw on the previous problem, we used BH3THF for that, anti-Markovnikov HOH, followed by H2O2 and NaOH. That was that hydroboration oxidation mechanism. You can look that up in your book for the exact mechanism of that. All right, the next one is a little bit hard to spot because it looks like you're taking that CH2 over here, right? It looks like you're taking that CH2 and you're replacing it with an O. But really what you're doing is you're cleaving that double bond. You're breaking off the CH2. It's gone. It broke off. What's left is the double bond that's in its place. The double bond O that's in its place. So since this is a ketone, we don't have to worry about whether an aldehyde is getting converted to a carboxylic acid or not. So again, we could use ozonolysis, O3 followed by DMS, dimethyl sulfide, or you could use KMNO4 cold. Okay. All right. We've seen this reaction again. Okay, we're adding the OCH3 there, the more substituted side, and we're adding an H there. So that's Markovnikov. The H is going on to the carbon with the most H's. So Markovnikov, we can do that with H plus and HOCH3. That same pattern. That was like HBr, remember? Like HBr. Okay, diols. Now, this is interesting. It might catch your eye that we've seen how to make diols. We've done syn diols and we've done anti-diols. Here, they're not indicating whether it's syn or anti because it doesn't matter. There's no stereochemistry involved. Neither of these carbons is a stereocenter. That carbon has two symmetrical ring groups, and this carbon has two H's. So there's literally no way to differentiate between the outcome if these OHs add syn or anti. You get the same product. There's no stereochemical difference. So you can use either method. You could use OSO4 and H2O2 or KMNO4 cold. Over here with the ozonolysis reaction, the alternative was or KMNO4 hot. Okay, so remember those do something different. Okay, here we're making this three-membered ring. Basically, we're taking the two carbons that we start with and we're adding this one carbon to it. We have not actually gone over that. We did do one where we put bromines on it like that. I I'm going to skip it for now. I'll give you the reference. It's called the Simmons-Smith. It involves making one of these carbenes. It's a C with two H's and a lone pair. It makes a carbene. Well, I'll let you look that up in the book, okay? Because we haven't talked about it. It's not a very common reaction. It's like super specific, that's all. That's what it does. It makes a 3-membered ring, a cyclopropane ring from an alkene. All right. The next one, okay, so we're adding an OH and a Cl across the double bond. And specifically, we add the OH to the Markovnikov position, and we add the chlorine to the anti-Markovnikov position. That was exactly what this halohydrin reaction did. Right here, this was halohydrin, Cl2 and H2O. Here they're adding anti. They always add anti. In the previous case, where was it? We've done so many of them. Here it was. The OH, right? The OH adds Markovnikov. The chlorine adds anti-Markovnikov. So they're anti to each other, where they have a specific regiochemistry as well. In this case, in this problem, again, there's no stereochemistry. Again, this carbon is symmetrical, and this carbon is symmetrical. So the fact that they add anti is not important here. You don't get a different product depending on whether they add anti or not. So we don't have to worry about it. But we do specifically have the Markovnikov for the OH and the anti-Markovnikov for the chlorine. And that is a sign that we need H2O and Cl2. We make the chloronium ion, that 3-membered ring. We pop it open with the water. That ends up being OH. And because the chloronium ring has a positive charge on it, that indicates that the water attacks the more substituted carbon, and therefore the OH ends up in the Markovnikov position. Okay. Interesting. Okay, so here we've got an epoxide, and you'll notice that the epoxide, this is a little bit tricky. I think they want 2 steps here. The epoxide is not where we expect it. The epoxide always adds across the double bond, and the double bond is not there. The double bond is here. Let me double check that this is a 2-step process in the book. Yep. Okay. So actually, it's 3 steps. So we have to basically move the double bond. Let's think backwards. Okay. Because I recognize that I can't do this in 1 step because the epoxide's in the wrong place. It means it's multi-step, and therefore I want to work backwards. So we'll say if the epoxide should be there, we could make that using MCPBA, our epoxidizing agent, if we had the double bond there. Right? Piece of cake, right? If we had the double bond there, then we can easily put the epoxide there. how could we make a double bond? We know how to make double bonds by elimination. So what if we had something like that with our bromine there, and then we do Zaitsev elimination, KOH and heat, so that we remove one of those H's or one of these. They're the same. It's symmetrical. Okay. But not, remember, not one of these. That would be Hoffman. If we wanted those red ones to go, we'd use a big bulky base, but we don't want those red ones to go. So we want the green ones to go, so we use Zaitsev, a small base. Okay, and we can get that bromine on there because from our starting material, that is the Markovnikov position, right? If we do HBr, the H will go where we want it, onto the carbon with the most H's. It'll go here. And the bromine will go there. Okay. That's Markovnikov. So this is kind of cool. We add the bromine to the Markovnikov position so that we can do Zaitsev elimination and move the double bond. And now we can do the epoxidation. Okay. There are other ways to do it. I'm just glancing at the answer key. It says alternately hydration followed by dehydration. So what they're saying is that instead of adding a bromine Markovnikov, you could add a water, and so you get OH there. And then you remove the H by a dehydration to get the double bond there again. The point is that we have asymmetrical control over this. We can control which side of the double bond we add to using either Markovnikov reactions or anti-Markovnikov reactions, and we can control what side we eliminate from using either a Zaitsev base or a Hoffman base. So that control over asymmetry gives us the ability to move things around a little bit. Okay, we start with a choice. We activate one of those sites, and then we can activate a neighboring site and do the epoxidation to it like that. All right. That is all. That is a lot of material. Hopefully you see the big picture, okay? Hopefully by watching how these problems are solved, you can hopefully see what kind of knowledge is needed. Okay. It'll help you. I'm hoping it'll help you say that if I only knew this stuff, then I could answer these questions. And then you go and you study that stuff. Okay. Whether it's mechanisms, whether it's big picture stuff, whether it's pattern recognition, whatever it might be, hopefully this helps you recognize what you need to study. Okay. Have a good night.